Hello. In today's lesson, we're going to try to find the derivative of x to the x. And initially, I want you to try this like a problem-solving session. I want you to try to find the derivative of x to the x. Use all the tools you have in your toolbox. Maybe take some guesses. Use whatever you have available to you. Try to find the derivative of x to the power of x. Okay, assuming you gave it a try. You might have gotten a bit stuck, but hopefully you came up with some predictions, maybe some guesses. I think one educated guess that seems reasonable is maybe the x comes down. Maybe this comes down to the front and you get x times x to the power of x minus 1. But some of you might have said, no, this looks like one of those rules we learned the other class with the logarithms. Maybe it's going to be x to the x times ln x. Thinking about it kind of like a to the x or 2 to the x. And maybe those rules are right and maybe they're not. What we can do is actually use Desmos to see if those rules are correct. So what we have here in Desmos is the original function, x to the x in red, and the derivative of f in blue. Now, if our answer was correct where we brought down the x times x to the power of x minus 1, we should get these two graphs matching up. Doesn't look good for us. Those two graphs do not match. So that's definitely not correct. Let's try the second one. X to the power of x times ln x. Perhaps that will work. Perhaps those graphs will match. Times ln x. Maybe a little closer, but still, those are not the same graph, and so neither one of those answers is correct. Unfortunately, I wonder how we find this derivative, x to the power of x. Well, let's take a look at a new technique we're going to learn. So the technique is logarithmic differentiation. Let's say we have a complicated function which involves products, quotients, and powers of other functions, functions to the power of other functions. To find the derivative of fx, we often take ln of both sides, then use properties of ln to simplify before we take the derivative. Oh, okay, so the advice I would give you here, and if you weren't able to get it, go ahead and pause the video and try. Try taking ln of both sides and see if you can come up with a derivative. Alright, assuming you gave that a go, let's take a look. We're going to let y equal to x to the x. So ln of y equals ln of x to the x. Bringing down the x, that could be x ln x. Well, now when we go to find the derivative, we get 1 over y dy dx using implicit equals a product rule, 1 times ln x plus x times 1 over x. Now I'm going to simplify that a little bit just to help us with plugging it in later on. So we have 1 over y dy dx equals ln x plus x over x is just 1. So dy dx equals y times ln x plus 1. And we should plug in for y. We know our y is x to the x. So x to the x, ln x plus 1. So that's actually the derivative. The derivative of x to the x is x to the x ln x, but there's also this plus 1 business going on in here. Let's go ahead and confirm that this is right on Desmos. So if we look here, we have the derivative of x to the x in red. And then when we type in our answer, x to the x times ln x plus 1, we have exactly the same graph. So indeed, this is the derivative of x to the x. And the way we found it was by taking ln of both sides, called logarithmic differentiation. Let's try another example here. fx is going to be equal to the 7th root of 3x squared plus 5 times cos x of 2x over the 5th root of x. Now, you could do this question using the quotient rule. But in the middle of the quotient rule, you're going to have a product rule. And in the middle of your product rule, you're going to have chain rules. And my goodness, this is going to get crazy. So instead, I'm going to try using ln. It's not as required. When you have x to the power of x, you must take ln. In this case, it is technically optional, but I want to show you what happens. When we take ln of fx, the other side now has an ln. So ln, I'm going to write this as a power. So 3x squared plus 5 to the power of 1 over 7 cos of 2x over x to the 1 over 5. The reason we do this, the reason we take ln, is notice we have things like multiplication. We have things like division. There are log rules that can be used in these situations. Ln of x times y is going to be ln x plus ln y, so the numerator becomes ln of 3x squared plus 5 to the 1 over 7 plus ln cos 2x. In the bottom, we can subtract ln of x to the 1 over 5. And then we have another rule still if we want to apply it. We can go ahead and take down those exponents. So we get 1 over 7 ln of 3x squared plus 5 plus ln cos of 2x minus 1 over 5 ln x. So this is still equal to ln of fx. I haven't actually done calculus yet. I've just simply taken ln and expanded it using log rules. Now I'm going to go ahead and do calculus. On the left-hand side, I'm going to get 1 over fx times f prime x using implicit. On the right-hand side, well, I'm going to get 1 over 7 is just a constant times 1 over 3x squared plus 5, chain rule, 6x, plus, I'm going to do the derivative of ln, which is 1 over cos 2x, times negative sine 2x times 2, minus 1 over 5, 1 over x. And so you can see very quickly all that product and quotient rule disappeared, and we just were able to do the derivative term by term. One term plus another term, subtract another term. Now there is this pesky business of the 1 over fx. We're supposed to find the derivative, f prime. And so we can't have f prime times 1 over fx. We need to isolate for it. So we're going to multiply both sides by f of x. And I'm going to write the f of x not as f of x, but as what it was initially. Fx being this thing up here. But other than that final step, we're done. So we write f prime x equal, we write fx as the 7th root of 3x squared plus 5 over the 5th root of x times cos of 2x, and then square brackets, and we recopy everything we had above. If you want, you're welcome to combine them into single fractions. This will be 6x over 7, 3x squared plus 5. This will be plus negative sine 2x times 2 over cos 2x. And then for that last one, we have minus 1 over 5x. Now, just because you can do logarithmic differentiation doesn't mean you should. Let's look at this question here. What if I were to do just regular derivatives? If I would have seen this question yesterday before I learned about logarithmic differentiation, I would have done product rule. 2x squared plus 17 to the power of 1 times 2x, and then leave the second function alone. So a little bit of product rule there and there, plus, leave the first function alone, x squared plus 17 to the 2, times 5x to the 4 plus 4 to the 4 times 4x cubed. And I would be done. There's my answer. And that is perfectly correct. There's nothing wrong with doing that question that way. In fact, that's the way you should be doing the question. This question is fine. There's no need to do logarithms. It's a perfectly valid question. But if you wanted to, you could say, instead, you're just gung-ho about those logarithms. You learned about them and you want to give it a try. So yeah, you can take ln of this side. And so you'll have ln of x squared plus 17 to the power of 2, x to the 4 plus 4 to the power of 5. Then you use your rules to split this up as ln x squared plus 17 to the 2 plus ln of x to the 4 plus 4 to the 5. You bring down your powers, so you get 2 ln x squared plus 17 plus 5 ln x to the 4 plus 4. And then you go ahead and do a derivative, and at this point I'm not going to bother finishing it off. You can. You're more than welcome. You should get the same answer eventually once you simplify and work it all out. But notice it's taking a lot more time, and in fact there's room to make mistakes if you're not careful. You really don't want to be using logarithm differentiation unless you absolutely have to. I'll give you a bit of a silly example here. That one maybe you might have used logarithms on, but this one, again, you shouldn't. And I'm going to show you that you could, just to show that you get the same answer. What's the derivative of sine x? Well, we know. Cos x. But maybe you say to yourself, no, I want to set y equal to sine x. I want to take ln of y equals ln of sine x. Now I want to use implicit, so I get 1 over y dy dx equals 1 over sine times cos. I keep going, so dy dx is equal to y times cos x over sine x. And I know that y is equal to sine x, so I have sine x times cos x over sine x. Cancel the signs, and I get cos x. Huzzah! You do get the same answer. It's math. You can't go wrong. Of course you'll get the same answer. But look at the amount of work. This is one line. This is 1, 2, 3, 4, 5, 6 lines. It's just not efficient. And so I would really recommend you think long and hard before applying logarithms for a derivative question. So let's take a look here. Which function should you use logarithmic differentiation on? What do you think? Sine x? The square root of x squared? X squared plus sine x minus 24 cotan x? Or cos x sine x secant cubed 2x over root e to the x ln x times 4x squared? I'll give you a second to think about it. Alright, so the answer should be obvious. It's indeed D. This is a complicated function involving lots of multiplication and division and powers. This is a function you'd want to use logarithms on, not any of the others. So let's do another example here. We have x sine x to the power of cosecant inverse of e to the 2x. On this example, you have to use logarithms because you have x in both the base and the exponent. And so that's something to note. Anytime you have x in the base and x in the exponent, it's not optional anymore. You must use ln. There's no way around it because we need to use ln to bring down that power. And I'll show you what I mean. We're going to have ln of y equals ln of x sine x cosecant inverse of e to the 2x, which we write as cosecant inverse e to the 2x times ln of x sine x. We use the wonderful rule that allows us to take our exponent and move it down to become a coefficient, because that turns power to a power, which we can't do in calculus, into multiplication, which is the product rule, which we can do. So let's go ahead and do the calculus. 1 over y dy dx is equal to, now we have a very messy product rule to worry about, so we get negative 1 over e to the 2x square root e to the 2x squared minus 1 times e to the 2x times 2. So that's our first portion. Then we leave the second one alone, ln of x sine x, plus, now we have to look at the derivative of that second one. So we're going to get cosecant inverse of e to the 2x times, well, this is actually going to need a bit of a product rule inside. We're going to have 1 over x sine x times derivative of x is 1, and derivative of sine x is cos x. So x times cos x. It's pretty long, but we've been able to do the derivative. The last step is we need to isolate for dy dx. So if you look over here, dy dx has an extra 1 over y with it. So we need to multiply that on both sides. And to save time, we know it's going to be a y over here when we multiply. There'll be a y there. And that y is this initial y from up here. So our final answer will be dy dx equals, we'll rewrite the y, x sine x cosecant inverse e to the 2x times, put big brackets and start to write everything else, negative 1 over e to the 2x square root e to the 2x squared minus 1 times e to the 2x times 2 times ln x sine x. Now we're going to do the plus for the other portion. Plus cosecant inverse e to the 2x times 1 over x sine x times sine x plus x cos x. And then putting big brackets to close off our answer. So let's go ahead and try a multiple choice question here. Determine the derivative of f of x equals x to the 6x. You're definitely going to need to take ln of both sides because you have x in the base and x in the exponent. So pause the video and give it a try yourself. Alright, hopefully you were able to come up with the correct answer, which is A. And I'll show you here briefly. You'd have ln of x to the 6x, which becomes 6x ln 6. When you do the derivative of that, you're going to get 6 ln x plus 6x times 1 over x, and this is going to simplify to 6. Which actually means that there's a 6 we could factor out of both of these terms. We could write this as 6 ln x plus 1. Remember, when we do this, we're going to have an extra y in the front, so our final f prime is going to be x, 6 to the x, times 6 ln x plus 1. And if you write that 6 in front over here, you have the correct answer, A. A little bit of simplification in algebra there to make sure your answer was correct, but as long as you were able to follow the steps, you should get the correct answer. Let's compare ln x squared and ln x squared. It's tricky. They sound the same when you say them, ln x squared and ln x squared. Maybe there's a bit of a pause with that second one, ln x all squared. What happens to their derivatives? Certainly, they're not the same function. The brackets are in a different place, so we should get different derivatives. And let's try the one on the left first. The derivative of ln x squared means ln x is the most outside function. So the chain rule says you do 1 over x squared and then times 2x, which we could simplify to 2x over x squared, or simply 2 over x. The derivative of ln x all squared, on the other hand, the most outside function is the power. So we use the power rule first, and then we use the derivative of the inside with the chain rule. Well, you could write that as 2 ln x over x, and those are clearly not the same. So we want to see here that these two situations are not the same. the brackets matter. Whether the brackets are around the x squared or around the whole ln, they're going to be a different answer, and you need to be very careful when you're looking at your questions, because you don't want to get tripped up and think that, oh, ln x is going to be 1 over if there's going to be a power applied to it first. Here we have a bit of a strange example. The derivative of ln x to the power of cos inverse of 2x. Now, I want you to acknowledge what's tempting, what you want to do. We see ln here, and we think to ourselves, log rules, of course, log rules. I could take that cos inverse 2x and I could just pop that on down to the front, because I know in log rules, when I have a power, it can become a coefficient. But that is incorrect. And again, this is referencing the previous example we just looked at. If the brackets were closer here, if we had x to the power of cos inverse and that was in brackets, maybe something like this, ln x to the cos inverse of 2x. Well then, certainly in this situation, we would be able to use log rules. There's a power on the x and we could bring that down to become a coefficient. But the brackets matter. If the brackets are not around the x, but instead are around the whole logarithm, this is a power on the whole logarithm, and we cannot use log rules. We're not able to bring this down to the front, which means we actually have to take the logarithm. We're going to have to do ln of both sides, which is kind of strange because there's already an ln there. So let's see what we get. So we have y equals ln x to the power of cos inverse 2x. So you get ln y equals ln of ln x to the cos inverse of 2x. Now we can move that down to the front to become cos inverse of 2x times ln of x. We're going to have an ln of x. Interesting. Well, let's do the derivative. 1 over y dy dx equals, the derivative of cos inverse is negative 1 over square root 1 minus 2x squared times 2. And then with the product rule, we leave the second function alone, ln of x, plus cos inverse of 2x times, now we'll be careful here. We need to peel that function one layer at a time. The derivative of ln x would be 1 over x. So the derivative of ln x is 1 over ln x times, of course, the chain rule, the derivative of the inside function is 1 over x. So our final answer would be dy dx equals, we multiply that y to give you ln x cos inverse of 2x. And then we rewrite all of this, negative 1 over square root 1 minus 2x squared times 2 times ln of x plus cos inverse of 2x times 1 over ln x times 1 over x. Now, we can use this knowledge of e and ln and their derivatives to actually prove something that we took for granted in the beginning of the course. Initially, I told you that we needed to use this, the number e, which I said was a special limit, 1 plus h to the power of 1 over h. I claimed that this was equal to e. We can now prove this. And it's quite an interesting proof, and it's very nice to see how this results in the number e. So here's our proof. We're going to let fx equal ln x, which of course means that f prime x is 1 over x. And therefore, if I wanted to evaluate f prime at, say, the number 1, I would get 1 over 1, or simply 1. So f prime of 1 is 1. Okay, what does that do for us? Well, if f prime of 1 is equal to 1, I could write f prime as a limit. F prime is the limit h approaches 0 of f of x plus h. So f of 1 plus h minus f of 1 over h. But f of x is ln x, so we can write that down as the limit h approaches 0 of ln 1 plus h minus ln 1 over h. If we remember from pre-cal, ln of 1 is equal to 0. So this simplifies yet again to the limit h approaches 0 of ln 1 plus h. ln of 1 is gone, it's just 0 over h. And let's keep going. I'm going to rewrite that h as 1 over h. 1 over h times ln of 1 plus h. And the reason I'm going to do that is I want to take that coefficient and hop it up to become a power. I want to do that rule in reverse. So here we'll get the limit h approaches 0 of ln 1 plus h to the 1 over h. Okay, well, apparently this thing, we know the derivative at 1. We know this limit is equal to 1. How does that help us? I showed that the limit as h approaches 0 of ln of this business is equal to 1. Well, what we can do now is we can take this limit and we can take e, or take exp of both sides. That means we'd have exp of the limit h approaches 0 of ln 1 plus h to the 1 over h equals exp of 1. exp, by that I just mean e. And if you notice, we have exp and ln. Well, e and ln are inverse functions of each other, so they just cancel out. So we're just left with the limit h approaches 0 of 1 plus h to the 1 over h equals exp of 1, or just e to the 1, which is just e. And there's your proof. The limit as h approaches 0 of 1 plus h to the 1 over h is indeed e, and this is how it's shown. Now, using this theorem, we can prove another theorem. We can prove that the limit as n approaches, in this case, infinity, of 1 plus x over n to the power of n is equal to e to the x. How would we prove this? To start, we're going to need a substitution because we want to use the previous result in some way during this proof. And in particular, we're going to let h equal x over n, that quantity x over n, because if you think about it, as n approaches infinity, h is going to approach 0. If you look at it, no matter what x value you pick, whether 10, 100, or 1,000, as n gets larger and larger and larger, the quantity x divided by n will get smaller and smaller and smaller. Eventually, this quantity approaches 0, and so we have h approaching 0, which means that we can rewrite our limit similar to the other limit. The only thing we have to do is figure out what this n will be. And so rearranging here, if h is equal to x over n, then n is equal to x over h, if we just cross multiply the h and the n. So what that gives us is the following limit. The limit as n approaches infinity of 1 plus x over n to the power of n is equivalent to the limit h approaches 0 of 1 plus h to the x over h. Now, for that, we almost have the limit that we had above. We just need one last technique here. We have x over h, and you could think about x over h and the exponent there as literally x times 1 over h, or 1 over h times x. And if you remember, power to a power we multiply. So if we have multiplication, we can turn it into power to a power. Limit h approaches 0, 1 plus h to the power of 1 over h, and then all to the power of x. Because if you multiply back power to a power we multiply, we get back to the x over h. Now that inside limit we know is equal to e. And then we leave the x as the exponent. And we're done. We proved that the limit as n approaches infinity of this quantity gives you e to the x. Now this is very interesting because what it means, and you could pick, for example, n equal to 2. So, of course, when n is 2, we're not close to infinity. But what it says is when, let's say, n is equal to 2, the quantity 1 plus x over 2 squared, apparently that's similar in some ways. That's similar to e to the x. If we expanded this, we'd have 1 plus x over 2 times 1 plus x over 2, which would be 1 plus, first, outside, x over 2 plus x squared over 4, which would simplify to give us 1 plus x squared over 4. Apparently, in some way, that's going to be related to e to the x. It's not going to be equal to e to the x because we'd have to make that power become larger and larger and larger, and 2 is a very small number. We're trying to approach infinity here. But this should give you a bit of a sense that even as n gets larger and larger and larger, you just FOIL it out, and you'd have yourself a polynomial. Somehow e to the x is similar to a polynomial? What's going on here? We need to investigate this a little bit further, so we're going to use some Desmos. So here we have the graph of e to the x in green, and we have our polynomial expression 1 plus x over n to the power of n. Now first we have just n equaling 1, which is a straight line because it would just be 1 plus x over 1 to the power of 1, which is just 1 plus x. But watch what happens as n increases. Very, very, very quickly, the polynomial begins to look almost exactly like e. Now we're only going to 20 here. And so if we were to up this number to say 200, well certainly we're going to get closer and closer and closer and closer. And even around 160, 170, 180, it's going to look indistinguishable from the graph of e to the x. Because we proved that as n gets closer and closer and closer to infinity, or as n grows without bound, as it gets larger and larger and larger, the graph of e to the x and the function 1 plus x over n to the n become the same thing. Which is very bizarre to think that we could use a polynomial to talk about e to the x. But this is actually something that happens in general in mathematics. So in fact, if you remember our friend Carl Weierstrass with his really crazy Weierstrass function, he actually went on to prove something in some ways much more useful. His initial function was continuous everywhere but differentiable nowhere, which seemed a little bit crazy, and maybe you thought he was only good for proving really bizarre examples, but Weierstrass came up with what's called the Weierstrass approximation theorem, and it states the following: every continuous function defined on a closed interval AB can be uniformly approximated as closely as desired by a polynomial function. So what this means is that the fact that we were able to take e to the x and approximate it with a polynomial as close as we wanted is not unique to e to the x. This is true for any continuous function. And because polynomials are among the simplest functions, and because computers can directly evaluate polynomials, this theorem has both practical and theoretical relevance, especially in polynomial interpolation, which is a way of using polynomials to fit other types of functions. The original result was established by Carl Weierstrass, our good friend, in 1885 using the Weierstrass theorem. Since then, it's been generalized by Stone in 1937, and a simplified proof was given in 1948, so it is now known as the Stone-Weierstrass theorem, which generalizes it to some more complex math that we're not too concerned about right now. But I'll show you some examples of this because it's very interesting to see how the Weierstrass approximation theorem, and in particular what's called the Taylor series, apply to things like sine and cosine. So let's go ahead and investigate our good friend Sine X. Now you need to study some more mathematics to actually figure out how to make these polynomials, in particular the Taylor series. But the point is we can just start writing polynomials, and so I'll tell you the polynomial to write. We have x minus x to the power of 3, and then I'm going to divide it by 3 factorial. If you look, it's actually pretty similar to sine x. And let's maybe go ahead and add another term to make it a better approximation. The key to these is you always have to add more terms if you want the approximation to look a little bit better. And so let's add x to the 5 over 5 factorial. Wow, that's looking pretty good. Maybe one more term here. You might see the pattern. We're going to subtract x to the power of 7 divided by 7 factorial. And if you zoom in here, on the interval that we're looking at, it's very, very close to sine x. If I was to zoom in a little bit more on this first period, it's hard to see where it diverges. Maybe after here, yeah, the approximation is not so good, but in this initial interval, the graphs are almost indistinguishable, and we're only at the number 7. If we were to continue to, in this case, we're using odd numbers, so 21 or 101 or 1001, we would get graphs that would be indistinguishable. Sine x, we could write it down as a polynomial. And if you've ever wondered how your calculator calculates sine x, this is how it does it. This is what sine is on the calculator. If you want to think of maybe one of the truest definitions of sine, it's a polynomial. It's an infinite polynomial with factorials on the bottom and odd powers on the top. Now, if we know sine x, we can actually find cos x. You might not think we could. How are we going to find cos x with just the skills we have available? What we do is we take the derivative, because we know the derivative of sine, of course, is cosine. And so I'm going to go ahead and put cos up here for us. And I'm going to start doing derivatives of each term. So the derivative of x is 1. The derivative of x cubed over 3 factorial, well, the 3 factorial is just a constant, so we'll leave that on the bottom. And we would get x to the power of 2, and a 3 would come down in front. 3x to the power of 2. Divided by, we have to keep that factorial there, 3 factorial. Because the derivative of a sum is the sum of the derivatives, we can just keep on adding. We're going to get 5x to the power of 4 divided by 5 factorial minus 7x to the power of 6 divided by 7 factorial. And again, if you look here, the graph of cos and this polynomial are almost indistinguishable. And you could actually simplify this, because 3 over 3 factorial would just simplify to, well, the bottom is 3 factorial, which is 3 times 2 times 1. So we could simplify it to just the 3's canceling, x squared over 2 factorial plus the 5 and the 5 factorial reduced to give us a 4 factorial on the bottom, x to the power of 4 over 4 factorial. And then we subtract x to the power of 6 divided by 6 factorial. Again, a nice pattern. You can see it's just going to be the even numbers on top, alternating signs, the even numbers on bottom in a factorial, and we have this beautiful approximation of the graph of cosine. Now just a couple more here, because this is so incredible. If we look at e to the x, there's another polynomial representation, different than the theorem we proved, again using the Taylor series. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and so on. This time you just take all the numbers. And if you look here, again, almost indistinguishable, at least at the very beginning. This polynomial and e to the x, they look like the same graph, which means if you were to plug in the number 1, you could plug in the number 1 for x. So plugging it in gives you 1 plus 1 squared, which is 1 over 2 factorial, 1 cubed over 3 factorial, 1 to the 4 over 4 factorial, and if you do that on your calculator, I encourage you to give it a try, you get 2.708 or 2.71. So if you're wondering for another way to find the number e, you just take all the factorials, put them on bottoms of fractions, add them up, and you get the number e. It's incredible that you could have this infinite way to add up numbers and get the number e. Now I know what you're thinking. Is this possible for pi? Well, indeed it is. So to do the same approach for pi, we take the function tan inverse. Tan inverse is approximated by x over x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7. So we take the odd numbers, and there's no factorial this time. Just the odd number powers over the odd numbers, plussing and minusing each time. And then I plug in the number 1 to that polynomial. So I get 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. Does anyone remember what tan inverse of 1 is? What angle gives 1 on the tan circle? Well, it's pi over 4. So this number, as we start to get closer and closer right here, this number is going to approach the number pi over 4. So if we multiply the whole thing by 4, we get 4 minus 4 over 3 plus 4 over 5 minus 4 over 7 plus 4 over 9. 4 is all along the top, which, well, we've only done a few terms here, so we're only getting 3.339. But if we do 500 of them, we get 3.14, the number pi. And so as we go closer and closer, you can add more and more zeros to this expression. 5,000, 50,000, 500,000, 3.14159. You begin to approach the number pi. And so if you wondered, how does your calculator know the value of pi? It's because of these things, because of these infinite polynomials, thanks to the Weierstrass approximation theorem, that allow us to take complicated functions like sine or e or cos and approximate them using simple polynomials. Now for homework, make sure you try questions on page 223, number 39 through 50. Thanks for watching.